Good evening. How many potholes have you run over in the past week? Or debris that you had to maneuver your car around to try to stay safe? Or that construction zone that's been under construction for the past year? Well, we know we have a serious problem. Today I'm going to talk to you about our nation's infrastructure, particularly our bridges, and how myself, a structural engineer, is working to engineer sustainable bridges. We have more than 600,000 bridges in the United States. However, the state of them is under concern. The average bridge is approximately 43 years old. So if we break that down, that means 4 out of every 10 bridges is approximately 50 years old. There are over 188 million trips that are taken daily across deficient bridges. It makes you wonder and beg the question, how many of you have driven over them? In 2016, the data show that 9% of the nation's bridges were structurally deficient, where we define structural deficiency as one or more deficiencies that a bridge might have that needs special attention. So the way things work is that once every 2 years, a bridge is inspected to make sure that it's okay. But we've noted that there are some serious problems. In California alone, we see the largest number in an urban environment with structurally deficient bridges. More than 87% of these bridges in California are structurally deficient. So what does that look like? Well, let's take a look at our infrastructure report card for America. I know, you see a lot of C's and D's. What if you brought home a report card to a parent or someone who was funding your education? It definitely raises the question. So for the survey for the infrastructure report card, we see aviation earned a grade of D, where U.S. airports serve 2 million passengers daily, a D grade. Wastewater, D+, knowing that the demand of wastewater and treatment plants will grow more than 23% by 2032. Dams, D. Schools, D+, where 53% of schools need improvements to reach good conditions. So now we move on to the bridges, C-. Again, 10% of these bridges are rated to be structurally deficient, where America's overall grade is a D+. That definitely raises a concern to me. So this is where you come in. Our current user pays about 18.4 cents per gallon for gasoline and 24.4 cents per gallon for diesel. This translates to that we have this highway tax fund that we're trying to increase these prices because we know that the investment in our infrastructure is insufficient. And this is where you come in. So we talk about these bridges, and we see every year we put these de-icing salts on our roadways, and we know that these de-icing salts will corrode these bridges. We know chemically that when we put salts on roads, that lowers the freezing point for any fallen snow or rain such that it would not freeze. So it makes you wonder, we build these bridges, we put these salts on them to make them deteriorate, and then we have to repair them again. Does that make sense? Well, I thought the same thing too. So how do we move forward to address this issue? Well, we know it's going to take more funding. We know it's going to take leadership. We know it's going to take proper planning, and moreover, it's going to take innovation. And that's where one day I said, Monique, how can we make our bridges better? To me, it doesn't make sense. We build, tear it down, need more money, have to build it again. So I said there has to be a better way that we can use engineering to design our bridges better. So that's what I did. So close your eyes for a minute. Can you imagine a bridge without steel? And you can open your eyes. Well, that's what I did. I got some funding for research to really look at bridges and how we can design them better using composite materials. These composites are made out of fibers and resin that are pultruded together to be really strong. In fact, just as strong as steel. They have advantages of being more flexible, stronger, and more durable. Because the main issue is if we put these salts on the road, it goes down and affects the steel that are within these concrete structures that deteriorates and then repeat this cycle. So if we have something that is corrosion resistant, where in the bottom left shows a picture of these bars that are like rods that can replace the steel. If we can replace them and engineer them in a way that they can work just as well, we can look at longer lifespans for these bridges, longer than 50 years. So yes, the investment using these composite or fiber reinforced polymer FRP bars costs a little bit more money on the front end, but in the life cycle cost, it would be more manageable and we won't be replacing bridges every 5-10 years. And at the rate we're going, where we're already $123 billion in the hole of where we need to be to keep up with repairs. So the concept is, for bridge deck, if you think about on the red, those are what you would typically see for the steel bars, that they're laid in there to make sure that it carries the tension, where steel is very strong in tension. And we have it coupled with the concrete, which is very strong in compression when you squeeze on it. So my whole idea was nothing novel, but let's just use these composite bars on the inside of a bridge deck, lay them like a lattice structure or a matrix on top of each other, pull on some of them so that they're really strong in their optimal capacity and tension, then pour the concrete in and see how these things perform. There are some challenges. With any good system, we have to look critically at how the whole system works. But these bars themselves have a high strength to self-weight ratio, about 10 to 15 times that of steel. Like I said, they're corrosion resistant, non-magnetic, and non-conducting. It's a no-brainer, is what I thought. They also have excellent fatigue characteristics. In other words, if you cycle them back and forth, they can go for longer periods of time, which is ideal for the bridge environment. So the whole concept is, we have these bridge decks, we put them together like Legos, we connect them with concrete to tie it all together. But the way in which we have to use this system, in the long ways on the bridge deck, we actually pull the bars in tension. So where we have there the dead end, that's where we actually lock in the bars on that one end and pull from the other end, which is called the live end, to stretch out these bars. You can think of it like a rubber band. We stretch it really, really taut. And then we pour the concrete in to basically seal it all together to make it this one great system. Another advantage in which the Federal Highway is also moving towards is what we call these prefabricated bridge elements and systems. In other words, these panels are perfect in the sense that we can make them off-site in a lab or a manufacturing plant or a precast plant, and then put them on a truck, take them to the bridge site, and then lay them in like Legos and then connect it all with the concrete. So the idea that it would take less time for construction and also be very efficient. So with these bars, we also learned that there are some thermoplastic properties that make these bars great. So one of the challenges with having these bars or composites, we know they're flexible, but will we be able to bend them like we can steel so that we can make hooks? Well, yes, you can. We can heat it up. We can hit on it with a slight loss of the cross-sectional area, and then we can bend it. So what advantage does this have? Well, it's a significant advantage in that we can have these bars also serve as hooks when we put the two panels together and need to connect it with the concrete in between. So right here you're seeing a picture on the inside view of looking at these bars that are these stirrups or hooks that we need to connect these bridge decks together and tie them together with either a grout or a high-performance concrete. So the question becomes, when we build this system, how will it work? Well, that's what we did. Through the research that I got through NSF, we were able to test this bridge deck system. So it's about 10 feet by 12 feet, a nice sized bridge deck, where you can see the yellow bars in the long direction are sticking out, and those are the ones that were pulled really, really strong. The other ones perpendicular to it were laid to give that lattice structure. So in doing so, we actually loaded down on the bridge deck, just how we would mimic the loads from a truck on a bridge, where we looked at several different cases. I mainly focused on load cases 1, where we have 2 wheels or a truck load wheels behind each other, and also load case 5, which is on the outer edge or what we're considering the overhang. In other words, what that load simulates is if you have a barrier on a concrete bridge, and then you have either impact from a truck or something, what's that overturning moment or that force that needs to be resisted? So we tested these. We had our control specimen that was made out of steel that was embedded in the concrete, as well as the bridge deck system, which you saw, which actually had the fiber bars that were pre-stressed or just pulled like a rubber band, as well as the other bars going perpendicular to that. So the solid line shows the aramid fiber reinforced polymer specimen, or the composite specimen, and then the control specimen is the one that's the dotted line. We see that if we were to look at just load in the vertical axis versus displacement on the horizontal axis, that the composite AFRP specimen actually took larger loads. It was quite strong, quite durable. We were very pleased with that. And that was for load case 1. If we had the loads on the inside of the bridge, or the top far right picture, where you can actually see that not only were the stresses and the loads transferred nicely, but it took a larger load. That's a win-win in my book. We took a step further and looked at the case where we actually have load case 5 showing here, where we have the control specimen as the dotted line, and then the solid black line as the composite specimen. So this is the worst case scenario, that if you were to have a truck or something that go off the edge, how much resistance would you get by the system? We see that the AFRP specimen, the fiber reinforced polymer composites, didn't do too badly. We see this, because the bars are quite flexible, this softening system where it still exceeds that minimum threshold for the load of 200 kilonewtons. So we had successful results with the bridge deck. And like I asked earlier, when I was thinking, how can we do this better? I extended it from bridge decks to also working on, now let's put these AFRP bars into a column to kind of go with this whole notion of this semi-metalless bridge system, so we can address this major issue of corrosion. So at Morgan State University, I've had several students and doctoral students working on this work, where we've taken it a step further, that innovation piece, where we have these bars that are addressing the issue of corrosion. Check, got that. But we also know that in several environments, these columns must also take some type of lateral loads, or maybe loads induced by earthquakes, which is a significant issue. We actually know that 2 of the largest earthquakes that happen in the United States happened in 1811 and 1812 in New Madrid, Missouri, right? That's not on the West Coast. The second one in 1886 in Charleston, South Carolina. We have different types of earthquakes on the East Coast. So while we address also this issue of corrosion, I thought let's also take it a step further in how we can build columns that are resistant to also absorb energy and can rock, but at very low levels, but still also be resistant. So that's what we're doing at Morgan State University. We're innovating. We're engineering systems to make them better and more sustainable to help America's infrastructure. That's the first phase. The second phase is that we're going to shake it up a little bit. We have a shake table that allows us to simulate earthquakes. The table is about 9 feet by 9 feet. We can mathematically input equations into the driving system and make this thing shake as if it were like a magnitude 8 or 9 earthquake at Morgan State University. So we're really excited to expand this research a step further to look at the dynamic loads so that we can put this all together and model it. So this is a picture of what the physical lab looks like in real time, with our strong floor and strong wall, for which we'll push and pull to simulate that softer rocking for that column. And then in the phase 2, we're going to put it on the table and shake it to also see its performance. So the question becomes, how do we really move forward? I had this idea to be innovative and to really try to engineer a more sustainable solution. But the fact of the matter is, it takes time. And it takes a paradigm shift, especially with the construction industry, to accept these different practices and say, yes, this is something that's more sustainable. Because we all can agree, I'm sure, that if we build something, use your taxpayer money to put salt on it, then have to build it back up, just doesn't make sense. But we know we have a long way to go. But the hope is that as we move forward, that we'll address these issues and also look at issues of asset management. Not only as we inspect the bridges and figuring out which bridge needs more help, but also to prioritize, well, which one needs more help first, so we don't see bridge collapses like we've seen in the past, where significant lives were lost. Thirdly, we also need to work on converting research to practice, of having more implementation projects, where we've had full-scale projects in the laboratory, but also having more field demonstrations, which would also help to move this forward, as well as policy. So with that, I thank you, and I'm glad to have shared my experience on how we've engineered better bridges. Thank you.